So the title of my talk is Axion Mass from Magnetic Monopole Loops. It's based on a paper put out last May and published in PRL with my advisor, Matt Reece, and my collaborators, JiJi and John Stout. And the central idea of our paper is that we find a new contribution to the Axion mass. But before I go into our contribution, I want to motivate it by discussing the more well-known case. So in the well-known case, axions couple to nonabelian gauge fields, and then they get a potential from instantons. So for example, the case of the QCD axion, we have an axion that couples to gluons in order to solve the strong CP problem through an AGG dual coupling. And this coupling is going to give the QCD axion a potential from instantons. Now in this case, the contribution can be computed in multiple ways depending on which regime we're in. So for example, in the high temperature regime, it can be computed using a dilute instanton gas approximation. And the low temperature regime, it can be computed using the Lagrangian, specifically from the mass terms in the Lagrangian. But when we actually measure, what we measure usually isn't the axion-gluon coupling because it's difficult to measure. Instead, we usually measure the axion-photon coupling. And that's what you can see in this plot on the bottom right from GitHub. It's a plot of axion constraints as a function of the axion mass on the x-axis and as a function of the axion-photon coupling on the y-axis. And really what I want you to get out of this is that there's a lot of time and money and effort that goes into measuring the axion coupling to the photon, which is an abelian gauge field. Now, in the case of the QCD axion, which also couples to a non-abelian gauge field in addition to the photon, the axion is still going to get a mass from that non-abelian gauge field. And for the standard KSVZ and DFSCUV completions, we know the relation between the photon coupling and the mass. It's given by these yellow lines on this plot. But what about the case where we have an axion that only couples to abelian gauge fields, in particular an axion like particle that only couples to abelian gauge fields? Do we know anything about its mass in that case? So that's what the goal of our paper is to answer. And what we find is that there is a new contribution from the coupling of the axion to abelian. In the case where the axion couples to abelian gauge fields, the axion gets a potential from loops of magnetic monopoles. Now, why do we expect monopole states in our theory? Why do we expect loops of magnetic monopoles? Well, in certain UV completions, we could actually just compute that those states should be there, for example, for certain guts. But more generally, Polshinsky in 2003 proposed the completeness hypothesis, what says that any UV complete theory of an interacting UN gauge field contains magnetic monopoles in the spectrum. And more generally, the lattice of possible charged dyon states, we expect it to be completely filled in quantum gravity. Now, I should point out that this contribution depends on virtual monopoles. So what's important is just that these states exist in the theory. They don't actually have to be populated. So the short version of how this potential comes about is that the Witten effect gives a theta-dependent mass contribution to heavy dionic states. And when we integrate out these heavy dionic states, that gives the axion theta a potential. Now, the whole talk is going to be dedicated to discussing this. So if this isn't clear yet, that's totally fine. I also, before I go on, want to make a distinction from previous work. So previously, there's a different contribution from the coupling of axions to monopoles and antimonopoles. In that case, we have a potential that's generated by the monopole-antimonopole plasma that was first brought up by Fischler and Preskill in 1983, as well as discussed in several more recent papers. And in that case, we actually have to have physical monopoles. So for example, generated in the early universe through the Kibble-Zurich mechanism. In our case, unlike this physical monopole-antimonopole plasma, we have virtual monopoles. So all we care about is that the states exist in the theory, not that they're populated. Okay, so outline for the rest of the talk. First, I'm going to review monopoles, dyons, and the Witten effect. Then I'm going to go through some of the details of our calculation. And then finally, I'm going to discuss phenomenology and future directions. So first, the Witten effect. The Witten effect tells us that monopoles in the presence of a non-zero theta acquire electric charge. So for those of you who are unfamiliar, the way to see this qualitatively is to imagine a magnetic monopole inside a region where theta is equal to 0, and surround that region by another region where theta is not equal to 0. And that's what you can see from this diagram on the left. You have this magnetic monopole, this dot in the center M. It's surrounded by a region where theta is equal to 0. And that's surrounded by another region where theta is not equal to 0. This line is just the boundary between those two regions. Now, the modified Gauss's law in the presence of a changing theta here is del dot E is equal to minus alpha over pi times the gradient of theta dotted with B. And all this tells us is that the magnetic field from the monopole induces an electric field when theta changes across this boundary. So the right-hand side of this equation is non-zero, which is going to give us a non-zero electric field. We also know, if we actually compute the electric charge, that it's equal to minus E theta over 2 pi, and that's independent of the size of this region where theta is equal to 0, which means that regardless of the size of this region, we still expect that this monopole is going to acquire an electric charge in the presence of a non-zero theta. So we can take the limit where the size of this inner region goes to 0, and it looks just like a monopole in a region where theta is not equal to 0 without this inner region, and we still expect this electric charge to exist. So that's the Witten effect. And that tells you qualitatively why we expect it. But in order to actually do our calculation, we're going to need to be a little bit more quantitative. And in particular, we're going to need the theta dependence of the spectrum of dyon masses. But before I go into the details of that, I want to give you a picture to keep in mind. So all of our formulas are completely general for various different monopoles, but the Hooft Polyakov monopole is a useful example to keep in mind, and it'll give you the correct results to leading order. So the Hooft Polyakov monopole shows up in the JiJi model. It contains an SU2 gauge field A, as well as an SU2 scalar triplet matter field phi A. And it has a potential that breaks the gauge group SU2 down to U1. This emits a monopole solution for phi A and A given here, where F and H are radial profile functions that minimize the energy. Now, this JiJi model, after breaking down to U1, has 4 symmetries. It has 3 translation symmetries, as well as a rotation around the unbroken U1. But the monopole solution is going to break those 4 symmetries. So in order to restore those symmetries, we're going to introduce the collective coordinates to parameterize the moduli, the space of monopole solutions. So we're going to introduce 3 translations x and 1 compact coordinate sigma. And this sigma is going to be the coordinate that we really care about. Sigma is going to parameterize going to be for the unbroken U1 rotation around the direction of the scalar. And since it's a rotation, it's a compact coordinate with period 2 pi. So in order to actually get the energy spectrum, we're going to need to quantize the moduli. And when we quantize the modulus sigma, it looks like a particle in a circle. So here we have the Lagrangian, we have a sigma dot squared kinetic term, as well as a theta sigma dot term. In order to get the energy of this, all we need to do is take the Legendre transform. Take the Legendre transform using the conjugate momentum to get the Hamiltonian, and then take the expectation value to get the energy. And what you can see is that this expression for the energy on the right depends on an integer n, as well as the value of theta in our theory. So we have a spectrum of dyonic states, which depend on this integer, which depend on this value of theta, that we're going to want to integrate out in order to get a potential for the axion. So how do we actually do this calculation? Well, there are 2 equivalent ways to get the axion potential. First, we can do a Coleman-Weinberg-like calculation. We treat the axion as the background field, and then we integrate out the heavy dyon tower. Second, we could also do equivalently a path integral over winding of the monopole around its collective coordinate. And these 2 pictures are related by Poisson-Reece summation, so they're going to end up giving us the same answer. In both cases, the effective potential B effective is calculated by summing over all disconnected backing paths that are topologically a circle. This is the analog of the closed string theory case, where we sum over insertionless tori. So here, V effective is equal to minus, the limit as V goes to infinity, of 1 over V times Z of S1, where V is the space-time volume, and Z of S1 is the transition amplitude for trajectories that return to the same point that they started at. So in order to get the effective potential, we need to actually compute Z of S1. The way to do that is using the path integral, specifically the free particle path integral. And when we actually compute the free particle path integral, what we find is that Z of S1 is going to be equal to the integral from 0 to infinity of d tau over 2 pi times some normalization factor that depends on tau times the exponential of minus m squared tau over 2. Now here, m is the mass of the particle that we're integrating out. So in this case, we want it to be the dyon mass. So we plug in our dyon mass spectrum that we computed earlier. M squared is equal to mass of the monopole squared plus m delta squared times n minus theta over 2 pi squared. Once we plug this in, we have an expression for the potential once we plug Z back into the expression on the previous page. But if we want to get this in terms of winding L, all we have to do is Poisson-Reece sum. So we plug in this formula for the Poisson-Reece summation, And what we find is that the effective potential looks like a sum over L times some mass-dependent contribution times e to the action of the cosine of L theta times some polynomials of the mass. So this is the final result, the result for the effective potential. One thing about this that I want to point out is that in the case of the Hooft Polyakov monopole, this instanton action actually reduces to 8 pi squared over g squared, which is interesting because it's exactly the same result we get in the Yang-Mills BPST instanton case, which is what we expect because we expect this result to be connected to that in this case. Okay, so we have the result for the effective potential. Now we can ask, what can we actually do with it? So I'm going to give you a phenomenological example where this is relevant. So the simplest example that you can consider is the case of a hidden U1 dark sector. So the U1 dark is gauged, and then we also have a spontaneously broken U1 Pesci-Quinn that's going to give us an axion. In this case, the axion mass is going to have 2 different contributions. So it's going to have this contribution, MA loop, that I've been talking about throughout the talk. And then it's also going to have a temperature-dependent contribution for the monopole anti-monopole plasma, which is previously known, and it's the contribution that I referenced earlier in the talk. And so the question we really want to ask is, when is our contribution the dominant contribution? And so that's shown in red on this plot on the left. So here this plot shows the x-axis is a function of the coupling, and the y-axis is a coupling of the function of the monopole mass. This blue line on the plot below it, blue solid line, is where the axion mass is too small because there'll be no oscillations today, so the axion can't be dark matter. And this green line is where the total dark matter abundance is equal to 0.12. So we need to be below that line in order not to overclose the universe. Here, sigma total is composed of both axions and monopoles. So you can see these dotted black lines show what fraction of that total abundance comes from axions. And so what I want really to get out of this plot is between this blue and green line, which is the valid region, there's quite a bit of that that's red. So in a lot of this region, our contribution is actually the dominant contribution to the axion potential. So it is phenomenologically relevant. Okay, so in summary, we point out a new contribution to the axion potential from loops of magnetic monopoles when the axion is coupled to abelian gauge fields. We know that this contribution is distinct from the previously known monopole and anti-monopole plasma potential. And finally, our contribution can be phenomenologically relevant. Of course, we've only considered a very simple model here. And part of the reason for that is because we haven't necessarily discussed all of the more complicated effects you can see when you have things like fermions in their theory. So one thing that we're currently working on in future directions is understanding the effect of light fermions, which we'd like to understand because we expect them in standard model. And why do we expect things to be a little bit more complicated with light fermions? Well, we know that the potential should vanish for massless fermions because we can rotate away the phase, so it should be unphysical in the case of massless fermions. And the way to see this is to notice that the theta dependence of the dyon tower is going to vanish because the spacing between the dyon levels is proportional to m delta squared. And m delta squared scales like the mass of the fermions, which goes to 0 as the mass of the fermions goes to 0. So in the massless case, we know that theta dependence vanishes, and therefore there's no potential. But what happens in the limit where fermions are light but not massless? We don't exactly yet understand how this works. So that's a current direction of research. Another question we might like to understand is how robust the assumption that V effective is dominated by single monopole loops is, because we haven't really discussed the effect of long-range Coulomb interactions. We expect they're probably subdominant due to the fact that we're working at weak coupling, but we'd still like to explore this more. So those are some current future directions that we're working on. Thank you for listening to this talk. If you have any questions about our work, you're welcome to email me or any of my collaborators.